Okay, let's now go to binomial random variables. So we've been talking about random variables. We talked about the mean of a random variable. We also call it the expected value. We talked about the variance of a random variable, the standard deviation of the random variable, which is the square root of the variance. And we also used Chebyshev's theorem to estimate certain probabilities when the mean and the variance of a random variable was known. Okay, now we're going to talk about a certain group of random variables amongst all different possible random variables. We're going to just identify one particular group. And basically this is just a generalization of the idea of tossing a coin several times. So in other words, if we toss a coin 10 times and we ask what's the probability that we get 8 heads, what's the probability that we get 5 heads, what's the probability that we get 2 heads, and so on, that kind of calculation. But that also, let's see, is basically the same thing as, for example, having a family of 5 children is like tossing a coin 5 times, and we can ask what's the probability of having 3 female children, or 4 female children, or 5 female children. It's basically the same kind of question as tossing a coin 5 times. What's the probability of getting 3 heads, or 4 heads, or 5 heads? So here's example 7, which we'll see in a little while. Toss a fair coin 12 times, find the probability of obtaining 9 heads, or another question would be at least 9 heads in the 12 tosses. But you can also see that, for example, okay, let's look at this one. Physical evidence shows that the probability of a given type of atom will split in a 24-hour period is this. So this is the probability that the atom will split. So if you basically collect 10 to the 30th of these atoms, which means basically taking it many, so it's not like 10 flips of a coin or 10 children, but this many atoms, but still it's the same idea. Find the probability that a certain number of them will split in the 24-hour period. So it's basically the same, again, the same question as tossing a coin, but here we would be tossing a coin 10 to the 30th times. But the calculation will be very similar. Or here's another example. We have 2,500 fruit flies. So this is like tossing a coin 2,500 times. Now this fruit fly larvae is subjected to radiation to induce mutations. Genetic evidence suggests that the probability of mutation under given conditions is this. So here's the probability of getting a mutation. The number of X mutations is this type of random variable that we're talking about. It's like I said, it's like tossing a coin 2,500 times and saying what's the probability that you get 10 mutations? What's the probability that you get 100 mutations? What's the probability that you get 155 mutations? And so on. Again, this calculation is very similar. In a certain state, mental cruelty is the legal reason given in 4 of 5 divorce proceedings. So here we look at 25 divorce cases. Again, it's like tossing a coin 25 times, and we are interested in the probability that we have, say, 5, that mental cruelty is the reason in 5 of these cases, or in 10 of these cases. Okay, these are all calculations that are very similar, and they're called, this is called a binomial random variable. All of these are examples of binomial random variables. So now the difference is, first of all, here we're talking about 25 cases, or maybe 25 tosses of a coin. Here we're talking about 2,500. In the other case, we were talking about 10 to the 30th. In another case, we were talking about tossing the coin 12 times. That's one difference, is the number of times we repeat it. And the other difference is what's the probability of the thing that you're interested in. So here we're interested in getting heads. The number of heads is 5, is 6, is 7. So basically the thing we're interested in getting heads. So what's the probability of that? Here we're interested in that an atom will split. So what's the probability of that occurring? Okay, so it's this number. Here okay, so anyway, these are all similar. These are called all examples of what we call binomial random variables. So let's study how to calculate the probability that such a binomial random variable will have a specific number of heads or a specific number of splits or a specific number of mutations or a specific number of times when mental cruelty is cited as the reason for divorce. So actually we're going to call each of these success. So getting a head we're going to call success. Having a split occur we're going to call a success. We need to call it either a success, one of them, either getting the head or getting the tail, success. The other one would be called a failure. Having a split could be called a success, and the other one would be called a failure, not having a split. Having a mutation might be called a success, and otherwise not having a mutation would be a failure. Having mental cruelty as the reason could be called a success, and otherwise a failure, and so on. So we're going to call one of them the success and the other one failure. Alright, so let's go to this discussion. So they say, in many experiments, we are primarily interested in whether a certain result does not occur. So heads or tails, mutation or not, and so on. For example, does a tossed coin show a head or not? Does an individual inoculated with a flu vaccine contract the flu or not? So here's another example. So we give vaccines to 20 people, and we count how many of them don't get sick, and we can say that each person is like a coin toss, and if they get sick, we could call that heads, and if they don't, we could call that tails, or vice versa. So we'll call one of the states success and the other state failure, sick or not sick, and so on. Or is an item selected from the output of a production process defective or not? So again, defective might be called success, or it might be called failure, and the other case would be called just the opposite. Or is it a girl or not? Again, the same idea. Experiments for which there are only two possible outcomes. Now, when we toss a coin, there's only two possible outcomes, but we're going to toss it 20 times, but we're doing the same thing repeatedly, and the thing that we're doing repeatedly has only two possible outcomes. So that's that kind of experiment where there are only two possible outcomes are called Bernoulli experiments. So what we're doing when we toss a coin 20 times is we could say we're repeating the Bernoulli experiment 20 times, or we're repeating the Bernoulli trial 20 times, also called a trial. It's traditional in statistical work to arbitrarily label one of the outcomes success and the other failure. For example, if we toss a coin, we might call head success and tail failure. The selection of the outcome to be labeled success is completely arbitrary and need not connote a successful outcome in everyday life. For example, an investigator studying the effect of a new drug for the prevention of malignant tumors in rats may possibly choose to call the appearance of a tumor as a success, even though one would not think of that as successful in everyday life. Okay, experiments with more than two outcomes can, if desired, be viewed as Bernoulli experiments by grouping the outcomes into two categories. For example, if we toss a die, now normally we wouldn't say that tossing a die is a has only 2 outcomes. We'd say it has 6 outcomes. It has these 6 outcomes. But however, if we call the outcome 3 a success and the other one's failure, then we can view this as a Bernoulli experiment with only 2 outcomes, success and failure. So we could look at it that way. Okay, so we could even sometimes treat tossing a die as a Bernoulli experiment, but only in this sense, where you treat one of the outcomes as success and all the others as failure, or vice versa. In a Bernoulli experiment, we use little p to denote the probability of success. So if we are tossing a coin and success is heads, we would use little p to indicate that the probability of heads. So usually that would be a half. But in the case of splitting an atom, it wouldn't be a half. Or what was it? The atom decaying, it wouldn't be a half. Okay, it would be some very small number. Would be the probability of the atom decaying. But but we're going to use p to stand for the probability of success, and then we're going to use q as the alternative. In other words, like if it was heads was success and tails is failure, we're going to use q to indicate the probability of tails. Okay? Since success and failure are the only 2 outcomes, then p plus q has to equal 1. Or equivalently, q has to equal 1 minus p. Now, if we're going to do this with the die, remember they suggested that we're going to call 3 success, and then all of these are going to be called failure. So we've got just 2 possibilities, success and failure. Then the probability of success is the probability of a 3, which is 1/6 usually. So we'll say p is 1/6 and q is 5/6. Many experiments consist of a sequence of Bernoulli trials. That's what we were saying. You have 12 tosses of the coin, or you have 2,500 larvae that you examine. For example, a single toss of a coin is a Bernoulli trial, and an experiment consisting of 5 tosses of a coin is a sequence of 5 Bernoulli trials. Examine the following problem. If a Bernoulli experiment is repeated n times, so maybe 12 times or 2,500 times, what is the probability of obtaining exactly x successes? So what's the probability of getting exactly 10 heads, or exactly 5 heads? Or what's the probability that 2,000 out of the 2,500 larvae mutate? So we'll put this in general terms and say we repeat it n times, and we're asking for the probability of obtaining exactly x successes in these n repetitions. So let's see how to solve this problem. And you can see that once we solve it, we'll have solved it for many, many different scenarios. So they say this problem is most easily solved when we assume that the trials are independent. Okay, so when we toss a coin, many times we usually always say that the tosses are independent, right? What happens on one toss, the second toss is not affected by what happened on the previous toss. Physically, this means we are assuming that the occurrences of success, S, or failure, F, in one trial has no effect on the chances of success or failure in any other trial. Mathematically, independence allows us to multiply probabilities, right? We know that. You know that the probability of A intersect B is equal to the probability of A plus times the probability of B if the events are independent. Okay, so it allows us, independence allows us to multiply probabilities. For example, if we have 3 independent repetitions of a Bernoulli experiment, where the probability of success on each trial is called P, then the probability of the outcome SSF means first success, success on the first, success on the second, and failure on the third, which would be denoted as the probability of success, success, failure, would be the probability of success, success, failure equals, we're allowed to split them up. Remember, this means success on the first and success on the second and success on the third. So that means, and failure on the third. So that means intersection. And intersection can be broken up into multiplication like this when you have independence. And so it's the probability of success times the probability of success times the probability of failure. But we called the probability of success P, and we called the probability of failure Q. So it's P times Q, or P squared Q. And the probability of the outcome FFF, that means F and F and F, which means F intersect F, which means probability of F times the probability of F times the probability of F, which this was called Q, so it's Q times Q times Q, or Q cubed. Okay, so this was the probability of success, success, failure. But there are other patterns by which we could get 2 successes. For example, the failure could come first and then the 2 S's. Or the failure could come in the middle. So it would be SFS. So usually we're not just interested in a particular pattern, but we are interested in asking the probability of getting 2 successes. This is one way to get 2 successes, but there are other ways. So they say, suppose now that we want the probability of obtaining exactly 2 successes in 3 trials, but not in a particular pattern like this, but just 2 successes. See figure 1. So here's figure 1. So we could get S, S, F. That would be one way. We could get S, F, S. That would be another way. We could get F, S, S. And that's the third way. I don't think there's any other ways to do it. Let the random variable x equal the number of successes in 3 trials. Okay, so now we introduce the random variable, and we let it be the number of successes in 3 trials. So remember that the sample space is basically has 8 items in it. So it could be SSS. A second possibility is SSF. Remember, if we write, I'm saying the sample space is this, if we're recording the sequence of successes and failures. So it could be this, could be this, could be this, could be this, and so on. And there are 8 different possibilities. There are 8 different elements in the sample space. But now we're only interested in the number of successes. So we define a random variable which goes from the sample space, this sample space here, these 8 possibilities without the p's here, these 8 possibilities, and we map those to just the number of successes. So this would be mapped to 3. So this one would be mapped to 2, because there are 2 successes in this outcome. This would be mapped to 2. This would be mapped to 1. This would be mapped to 2. This would be mapped to 1. This would be mapped to 1. And this would be mapped to 0. Okay, so remember, a random variable maps, there's a function basically, from the sample space to a set of numbers. The set of numbers here would be 0. You could have 0. You could have 1 in several cases. You could have 2 in several cases. You could have 3 successes. Okay, so we're creating a random variable that tells us the number of successes. So they say, let the random variable x equal the number of successes in 3 trials. From figure 1, we see that the probability that x equals 0, we're going to ask that. What's the probability that x equals 1? X equals 2, probability. X equals 3, what's the probability? So the probability that x equals 0, there's only one case. That's when we had, what was it, all males, I think? Or sorry, all failures. So that was q times q times q. Q squared here. The probability of failure is q squared, q cubed, I'm sorry. And then what's the probability that x equals 1? Well, we saw, did we see it before? Which was the one we saw? Sorry, this was SS, so this was s equals, probability that x equals 2. So here, the probability that x equals 2, we saw that if it was SSF, it would be p squared q. But we said that there are other ways that you could get 2 successes. So let's check that. So we could have SSF, we could have this one, and we could have this one. But notice that the probabilities are all the same for each of them, because you have PPQ here, but this one you have PQP, but still that's the same thing, p squared q. And here you still have, or rather here you have QPP, but still that's p squared q. So each time you get p squared q, then there are 3 different ways. So we say that it's 3 times p squared q. And if you think about it, this is an example of mutually exclusive, and that's why you add this probability and this probability and this probability. That's why you can add them, because they're mutually exclusive. So you can think about that to make sure that you understand that that's why we add, and that's why it's 3 times p squared q. Okay, so that's this one. You could do the same thing for this one. You get pq squared, and here you get p cubed. This one was q cubed. Okay? Therefore, the probability of exactly 2 successes is this one. Okay, so we have this result. Okay, so now they take an example. A fair die is tossed 3 times. Now remember, a fair die, we don't usually think of it as a Bernoulli trial, that is, where there are only 2 outcomes, but we're going to kind of define it in such a way that so that there are only 2 outcomes. So the question is, what is the probability of obtaining exactly 2 4s in 3 tosses? So first we have to define success and failure in such a way that there's only 2 possible outcomes to this tossing of a die. So what we're going to do is we're going to say what? That a 4 is success and anything else is a failure. So we have only 2 possible outcomes. So on each toss of the die, let success indicate that a 4 is tossed and failure that a 4 is not tossed. Thus the probability of success is 1/6, because there's probability of 4 is 1/6, and the probability of not 4 is 5/6. Since the tosses are independent, right? Tossing a die, the tosses are independent, usually we say that, we may use the results of 1, where the random variable x is the number of successes in 3 trials. So we already discovered that if that the answer is going to be this here, basically here, because we already found out that the probability of getting 2 successes will be this. But now we just have to fill in what p and q are. So p was, in this case, 1/6, and q is 5/6. So we get 3 times 1/6 squared and times 5/6. So this is the answer, 5/72. In the die tossing experiment of the previous example, find the probability of obtaining no 4s, obtaining exactly 1 4, and obtaining 3 4s. Okay? So we already did the calculations basically up here. We had that x equals 0, x equals 1, x equals 2, x equals 3. So x equals 0, in this case, would be getting no 4s. X equals 1, in this case, would mean getting exactly 1 4 in 3 tosses, getting exactly 2, we just did that, and getting exactly 3. So we just have to do q cubed, 3p q squared, and p cubed. So probably this one is q cubed. X equals 0 means no 4s. The probability of getting no 4s when you toss a die 3 times is this. The probability of getting just 1 4 when you toss a die 3 times is 3p q squared. It's this 1656 squared. It's this number. And the probability of getting 3 4s is just p cubed, which is 16 cubed, which is this number. So they say the problem is easily solved with the aid of the tree diagram, and one can be used to determine the probability of x successes in 3 independent trials for any problem with 3 independent Bernoulli trials. If there are more than 3 trials, then the tree diagram can be extended. However, the tree becomes unwieldy, so we must explore another method of obtaining the above results. Now, in the next discussion, we're going to be considering things like this. And this is the number of ways of selecting 2 items from a set of 3. Let's see if they give us an example. This was covered in a previous chapter in this book, a chapter on what's called counting and permutations. They don't really give you an example, but let's see. We can say that there are 3 tosses, so there are 3 spots to choose from, and we want to choose 2 of those spots to put successes. So we want to know how many different ways can we choose from the 3 spots, from the 3 slots here. There's 1, 2, 3 slots. How many different ways can we choose 2 of them? And that's exactly what this gives us. Okay, so this will be, how many ways are there to, if you have 3 slots, can you choose 2? Well, you could choose the first 2, or you could choose the first one and the last one, or you could choose the last 2, and those are the only ways. So we can say that we're choosing the 2 spots to put the successes in, and the other one will be failure. So how many ways can we do that? How many ways can we choose the 2 spots to put the successes in? And we see that there's this way, or that we can choose the first and last one, so there's this way, or we can choose the last 2, and so there's this way, and so there are 3 ways, and this gives us that this would have told us that there were 3 ways to choose 2. So they say, note that to obtain exactly 2 successes in 3 trials, we have the cases this, this, and this. In other words, there are 3 cases with exactly 2 successes out of the 3 trials, or 3 different ways of choosing 2 places out of the 3 for the successes to occur. For each arrangement, the probability of its occurrence is the same. It's p squared q. We saw that. By the counting methods of Chapter 7, there are C32 ways of making such a choice. Now, if you're not quite sure about this, you have to go back and look at this somewhere and understand it. We're not going to go through it here. So we can write it like this. The probability of getting exactly 2 successes, there are 3 ways of getting exactly 2 successes. So it's going to be, so remember, this is going to be from here to here, just these from here to here, is equal to 3, actually. And then with each of those, we have a probability of p squared q. So it's 3 times this, which we already saw. This calculation is actually 3 factorial over 2 factorial, 1 factorial. This turns out to be 3. So it's this times this. So this is the probability of getting exactly 2 successes. Now, so that's the way this works. Here, the probability of getting exactly 0 successes could be written like this. Now, we already did it. We already knew that the answer was q cubed, but it could be written like this. How many ways can we choose from the 3 slots? We have one place, another place, and another place. We could have like SSS or SFS or whatever. So there are 3 slots. How many ways of choosing from the 3 slots either of selecting 0? So there's just one. So this calculation here is 3 factorial 0 factorial 3 factorial times the q cubed. So it's 1 times that, which is q cubed. Then we can also do this one, the probability of getting exactly 1 success. That's going to be C31. And then the probability of 1, and then it's going to be PQ cubed. Okay, so it will be like this. And 3 will be like this. So you can see the pattern here. The 3 comes from the number of times that we toss it. And then the 0 comes from here, or the 1 comes from this question, or the 3 comes from this question. So the 3 comes from the number of times that we toss the coin or toss the die or repeat the experiment. And then this is the number of successes that we're trying to calculate, that is the 3 here. And then this is the probability of getting any one of the ways of, for example, 3 successes. Actually, in this case, there's only one way. Okay. So let's look at this one. Assuming the probability of success in a single trial of a Bernoulli experiment is p. So we're not talking about what the experiment is here. We're just saying assume that the probability of success is p. Find the probability of exactly 4 successes in 10 independent repetitions of this experiment. So now we're doing 10 repetitions, and the probability of success is p. Okay? So one way of obtaining exactly 4 successes is to have the first 4 as success and the last 6 as failure. Another way is this. You still have 4 successes in here. And still another way is this. Observe that each of these results is an arrangement of the 4 S's and the 6 F's. Obviously, the number of different ways to obtain 4 successes is just the number of different ways to arrange the 4 S's and the 6 F's. So you could arrange the 4 S's like this and then the 6 F's, or you could do it like this, or you could do it like this. It is evident that such an arrangement is completely determined once we specify the 4 positions where the S's occur. So if I say, okay, the 4 S's are going to occur at the beginning, then the F's will be everywhere else. Or if I say the 4 S's are going to occur at the first, second, 6th, and 8th, no, what is that? First, second, 5th, and 7th places, then we know where everything else is F's. So all I have to do is say where the S's are, and then I've specified one possible arrangement. So we can say that the number of arrangements with 4 S's and 6 F's is just the number of ways of selecting 4 positions for the S's from the 10 possible ones. Therefore, the number of such arrangements is C10-4. How many ways can we choose 4 slots from the 10? 4 slots to put the S's in. And the answer to that will be 10 factorial over 4 factorial times 6 factorial. This 6 comes from 10 minus 4. It's this minus this. So this turns out to be 210. Consequently, the probability of getting exactly 4 successes, well, we said with each one of them, getting exactly 4 successes is the probability of this one, plus the probability of this one, plus the probability of all the other ones. There's going to be 210 terms here. But for each term, the probability of this is going to be what? You're going to have 4 s's and 6 f's, so it's going to be p to the 4th, q to the 6th. Here, again, you're still going to have 4 s's and 6 f's, so it's still going to be p to the 4th, q to the 6th. And remember that we use independence to do these calculations. So this one, why is this p to the 4th, q to the 6th? Because it's the probability of s times the probability of s times the probability of f times the probability of f times the probability of s, and so on. And so that's that's p to the 4th, q to the 6th. Okay. So how many of these terms are there? 210. Each one has probability p to the 4th, q to the 6th. So it's going to be 210 times p to the 4th, q to the 6th. So that's the probability of getting exactly 4 successes in 10 repetitions. So suppose we translated this into a concrete example. For example, tossing a coin. If we want to toss a coin 10 times, and we want to know the probability of getting 4 heads, it would be what? 210 times the probability of heads, which usually we write as a half, to the 4th, and then the probability of tails, which will also usually be a half, to the 6th, and that will be the calculation. Okay, now we generalize a little bit more, and we say if the probability of success in a certain Bernoulli experiment is p, we did that before, what is the probability of obtaining exactly x successes in n independent repetitions of the experiment? So it's exactly the same as before, but we're just doing it a little more generally now. One way of obtaining exactly x successes in n repetitions is to have the x successes immediately, followed by n minus x failures. So you would have s successes, and then since we're doing this n times, the rest would be failures, means there's n minus x failures. The other ways of obtaining x successes can be obtained by rearranging these x s's and the n minus x f's. As illustrated in example 4, there are c, n, x different arrangements of these letters. Since each of these arrangements has x s's and n minus x f's, the probability of each arrangement is going to be p to the x, q to the n minus x. For example, the probability of this one is we have x of these s's, so it's probability, remember these are each p, and then these are each q. So we're going to have p to the x and q to the n minus x. Like this. We're going to have x of them are going to be p's, and n minus x of them are going to be q's, so we get this. So finally, we have this result. The probability of exactly x successes in n independent repetitions of a Bernoulli experiment, so we're repeating it n times independently, where we call success, the probability of success p, and the probability of failure is q, then the probability of getting exactly x successes is c n x, p to the x, q to the n minus x. Okay, so then we can use this in all of those other examples that we talked about the splitting of the atom, or the mutation of the larvae, or the divorce cases, and so on. We can use this formula. Find the probability of obtaining exactly 4 successes in 10 independent repetitions of a Bernoulli experiment if the probability of success on each trial is 0.6. So here in this question, n is 10 and p is 0.6. This p is 0.6, and x, they said exactly 4 successes, so x is 4. So you just fill those in here and you get the answer. So they fill them in, they get the answer, which is this, 0.111. Now we use the word binomial experiment and binomial random variable to give a name to these things. So they say that an experiment that consists of n independent repetitions of a Bernoulli experiment, so that's exactly what we've been talking about, is called a binomial experiment. So we do the experiment of tossing a coin 10 times. That would be called a binomial experiment. Or we toss it 20 times. That would be called a binomial experiment. If the random variable x denotes the number of successes in a binomial experiment, then x is called a binomial random variable. So all of these cases would be called binomial random variables. Now, sometimes we have tables for this, but you don't really need tables. You can easily do this with Excel or something. But here's a table that gives you the probability. So let's just learn how to read this table. Okay, so this gives you the probabilities for these calculations that we'd like to do. So for example, here's n. So this is the case where n equals 10. So that means that this is the part of the table. You can look for a binomial random variable table on the internet. I'm sure you'll find them, and you'll scroll down and look for the case where n equals 10, and then x is the number of successes in 10 repetitions. So x can be as small as 0, and it can be as large as not just 5. It could this is just a part of the table. X could go up to 10, right? If you toss a coin 10 times, you could get 10 successes or 10 heads. So this is just the part of the table that goes from 0 to 5 here. And then the result, the probability, is certainly going to depend on the probability of success. So like if you're talking about a fair coin, you'd be using probability of success as 0.5. In this example, the probability of success is 0.6, I suppose. So you could, and they're asking probably for the probability of getting 4 successes in 10 repetitions, where the probability of success is 0.6, and the answer would be 0.111. I guess that's the example they just did. Okay? So that's how you would use this table. And if you want, you can just verify these are the steps. Okay, let's try this one. Toss a fair coin 12 times. Find the probability of obtaining at least. Okay, now this is new. In all the previous examples, they were asking for find the probability of obtaining exactly something like exactly 9 heads. But here they've changed it. Here they say at least 9 heads. So what's the difference? Well, at least 9 heads means 9 heads, or 10 heads, or 11 heads, or 12 heads. So actually we have to do 4 similar calculations. So we have to do one for exactly 9 heads, and then another for exactly 10 heads, and then another for exactly 11, and another for exactly 12. So they say the solution is if x denotes the number of heads in 12 tosses, we are interested in the probability that x is greater than or equal to 9. So before we were interested in x equal to 9, for example. Now we're interested in the probability that x is greater than or equal to 9. Or equivalently, the probability that x has one of the values either 9 or 10 or 11 or 12. The probability of a head on each toss is 0.5. From the table, so you could look up a table. Let's see, can I find one? So if you look for this binomial table, I think I must have spelled it wrong. So here's one here. This one is different. This is actually related to the question we're currently asking, but it's different than the table we saw. Let's see if they have the this is called the cumulative one, but we want not the cumulative one first. We'll look at the cumulative one in a minute. This is not the one we want. Okay, so here's one. This is the regular binomial table. And so here we have n, the number of tosses, and R is the number of successes. We were using X, but we could just call it R. And here's the values for P. Now going back to this, so the probability that X is greater than or equal to 9 is equal to the probability that X equals 9 plus the probability that X equals 10 plus 11 plus 12. And then we check each of these. Let's try the first one. X equals 9. So we're talking about N equals 12 and X equals 9 and P is a half, right? So let's see. So N equals 12 here, X equals 9 or R equals 9, and P equals 50, 0.5 is here. So the answer is what? 0.54. I'm sorry, 0.54. Wrong. 0.054. Okay, let's see. Wrong. Oh yeah, here. 0.054. And you could do the other ones as well. You add them up and you get this. This is the probability that X is greater than or equal to 9. That means the probability that we get at least 9 heads. Okay, now they go to all the examples that we mentioned earlier, and they give us one warning. In each of these examples, we assume that the trials are independent. So here's the one about the atom splitting, and they say to see this as binomial, they say to see this, imagine that each atom in turn is observed for a 24-hour period, and let success indicate that the atom splits. Thus X represents the number of successes in this many trials or repetitions of the Bernoulli experiment, where the probability of success in each trial is this. Same thing with the fruit flies and divorce cases. These examples, diverse as they are, all follow the same basic pattern. In each situation, we can interpret the problem as a repetition of a simple Bernoulli experiment. It's important to keep in mind, however, that in order to have a binomial experiment, the trials must be independent. In each of the trials above, we assumed the trials were independent. In many physical problems, however, the assumption of independence is not warranted. For example, suppose medical records show that 40% of all U.S. citizens will contract German measles, it's a kind of measles kind of sickness, by age 25. What's the probability that in a group of 6 people, more than 25 years old, exactly 2 have contracted German measles at some time before their 25th birthday? If we let success indicate that the individual has contracted German measles and let X be the number of successes in the group, then we might argue that we have 6 repetitions of a Bernoulli experiment. Each person is an experiment. We have success and failure, getting measles and not, where the probability of success on each trial is 0.4. If we assume the trials are independent, then X is a binomial random variable. And from the table, the probability of success, the probability of exactly 2 in 6 contracting German measles is this. Or we could do the actual calculation using the formula that we saw above, but we could also use the table. However, let us examine the independence assumption. Suppose the 6 people selected are brothers who live in the same house. Since German measles is contagious, it's evident that if one brother contracts the disease, then the chances that some of the other brothers will also contract it are greatly increased over the national probability of 0.4. Thus, success or failure on one trial affects the chances of success on the other trials, so that the assumption of independence is unwarranted. If, on the other hand, the 6 people selected are not from the same family, then the independence assumption would be warranted if we knew that the 6 people had no direct contact with one another and had no indirect contact through mutual acquaintances who might have carried the disease from one individual to the other. Okay, if x is a binomial random variable, then x can be interpreted as the number of successes in n repetitions of a Bernoulli experiment with success probability p. Since x is a random variable, we can ask for its expected value, mu, and its variance. Remember, we went through earlier sections of this chapter where we came up with formulas for the mean of a random variable or expected value of a random variable, which we denoted as mu, and the variance of a random variable, which we denoted as sigma squared. So since these are random variables, we can ask what are their means and what are their variances. Although we omit the mathematical details, it turns out that the expected value of x is just going to be np. P is what? Just the probability of success, and n is the number of repetitions. Now, you have to prove this formula, and you have to, if you recall, the formula for expected value, it looks something like this, or it looks like this. So it's sigma x, I goes from 1 to n, x sub I, p of x sub I. Remember, it was the value of the random variable times its probability. Okay, so let's think about this. If we have, if we're repeating an experiment 10 times, like tossing a coin 10 times, then we're going to have what? The value of the random variable. What's the first value that that random variable can take? We could have 0 heads, so this could be 0, and then the probability of getting 0 heads. Now this, we have to use the calculation that we developed up above. I can't go to it right now, but the calculation, remember, it was cnx p to the, what was it, x q to the n minus x. So that's, we're going to have to use that here each time. In each one of these terms, we're going to have to use that. So this would be 0 times the probability of getting 0 successes, then 1 times the probability of getting 1 success. You'd have to use that formula for that, and keep going all the way until you got to the n terms. So in this case, you keep going from 0 to 10. Now, if you fill all of that in, and you do a bunch of algebra, it turns out that this whole long calculation can be simplified all the way down to just np. So you could have 10 terms here, you could have 100 terms here, but you could still simplify it so that the total long calculation is just going to end up with np. Okay? So that the expected value for a binomial random variable where we do n repetitions and the probability of success is p, is just going to be np. Okay? So it's kind of amazing that we can simplify all these long sums to just np. On the other hand, it's completely obvious, if you think about it, that the answer is np. For example, let's say we toss a coin 10 times. So n is 10. This is 10. And the probability of success, we'll say, is 1/2. So what's the expected number of heads? Or the expected number of successes? It's obviously going to be 5, which is 10 times 1/2. So on the other hand, it's completely obvious that it should be np, but kind of amazing that this long calculation that we derived for expected value will reduce to np. Okay, now we also can, if you go back and remember what the expression for the variance is, I'm not going to write it here, but you can go back and check it. It turns out it's going to be an even messier expression up here, but it turns out that it reduces to just NPQ. Okay, so that is not as obvious because we don't have any particular notion for what variance is, so we're not going to have any intuition about what it should be. Like here, the mean, we had a strong intuition about what it should be. But anyway, it turns out to be NPQ. Okay, where of course Q is 1 minus P. So as some examples, if x is a random variable with n equals 48 repetitions and p equals 1/4, then the expected value is going to just be 48 times 1/4, which is 12, and the variance will be 9. Now remember that the variance gives you some kind of feeling for the spread of the random variable. So this random variable would have a spread of 9. Usually it's the square root of the variance, or just sigma, which we would say is an indication. So we would say the variance, the standard deviation is 3. That's a kind of indication of the spread. Okay, let's look at an example here. If x is a binomial random variable with n equals 48 and p equals 1/4, then the expected value of expected value of x is 12, and the variance is NPQ, this equals 9. And this one, let x be the random variable that denotes the number of defective resistors in a sample of 2 resistors selected independently from a production process in which 5% of all resistors produced are defective. So the word that they're selected independently allows us to use to treat this as a binomial random variable. So the probability of, since the resistors are we can interpret x as the number of successes, we're going to call defective successes. The question is, where's the question? Just what's the expected value and what's the variance. So to calculate the expected value, the probability of success, meaning the probability of getting defective, is 0.05. So it's just 2 times that, which is 10%. The expected number of defective is 0.1, which they say agrees with the solution in example 4 in section 9.2, which I guess where we actually calculated it the long way using the formula for this. And then the variance is by equation 5 NPQ, which is this, which also agrees. Okay, here are some problems that I recommend you take a look at, and I will try to post the answers to the odd-numbered problems for you to check. Next section will be the normal approximation to the binomial.